The evaluation directive originated 3 days prior to Jabs' arrival at Rechlin on August 14, 1943, at 2,215 hours. Jabs returned to IVN-JG-1's operations facility at Lüneburg, following a successful night interception mission. The mission had resulted in destruction of 2 RAF Avro Lancaster bombers over Hamburg at 49th and 50th, confirmed victories according to unit records. Such success was typical for experienced night fighter crews equipped with airborne radar systems that allowed effective interception in darkness. A teletype message awaited Jabs in the operations room. The communication, originating from Luftwaffe High Command, directed him to report to Rechlin Test Center at 0800 hours on August 17th for combat evaluation of captured enemy aircraft. The message's classification level and priority designation indicated unusual importance. Standard procedures did not involve pulling operational combat pilots from frontline units for test center evaluations. Such work typically fell to specialized test pilots assigned permanently to evaluation facilities. The unit's staff captain expressed concern about removing an experienced pilot during intensive operational periods. Hamburg raids had intensified following the catastrophic firestorm attacks of late July, and night fighter units were conducting maximum effort operations. Losing a pilot of Jabs' experience, even temporarily, reduced unit combat effectiveness. However, High Command directives allowed no discretion. The evaluation was designated priority status. Jabs departed Lüneburg on August 16th aboard a Junkers Ru-50 to transport aircraft. The Ru-52, Germany's primary transport aircraft, provided regular courier and personnel transport services between Luftwaffe facilities. The flight to Rechlin covered approximately 200 kilometers, requiring roughly 90 minutes in the Ru-52's cruising configuration. Rechlin Test Center represented the Luftwaffe's primary aircraft evaluation facility. Established in the 1920s and continuously expanded through the 1930s, the facility occupied approximately 400 hectares. Infrastructure included multiple hardened hangars, outdoor test ranges, wind tunnel facilities for aerodynamic research, engine test cells, armament ranges, and extensive laboratory spaces. The facility's mission encompassed testing new German aircraft designs, evaluating captured Allied equipment, and conducting technical research supporting Luftwaffe operational requirements. Upon arrival, Jabs was met by Hauptmann Klaus Becker, identified as Senior Technical Officer for the Captured Aircraft Evaluation Program. Becker's initial briefing emphasized security classification. The P-38 evaluation was designated Geheim Kommandos Asika Command Matter, the highest routine classification level. Jabs was explicitly prohibited from discussing evaluation details with anyone outside the facility, including his own unit commanders. Without specific authorization from Luftwaffe High Command or Reichsmarschall Hermann Göring personally, the security emphasis suggested the evaluation's importance extended beyond routine technical assessment. Captured Allied aircraft were regularly evaluated. At Rechlin, the facility maintained examples of British Supermarine Spitfires, American P-47 Thunderbolts, and various bomber types, all bearing Luftwaffe test markings for evaluation purposes. However, most evaluations did not warrant Geheim Kommandos classification or direct high command oversight. The P-38 Lightning occupied Hangar 7 at positioned under high-intensity lighting for detailed examination. The aircraft's capture circumstances, according to facility records, involved an emergency landing in occupied France during March 1943. The pilot had experienced mechanical difficulties and successfully executed a forced landing in a field, allowing German forces to recover the aircraft with minimal damage. Such captures were relatively rare. Most combat-damaged aircraft either crashed catastrophically or were destroyed by their crews to prevent capture. Becker provided Jabs with a comprehensive technical dossier compiled from Rechlin's testing program. The document detailed aircraft specifications, performance data from flight testing, and engineering assessments of construction methods and design features. Becker's instructions emphasized seeking operational assessment from a combat pilot's perspective rather than engineering analysis. Facility engineers had already documented technical characteristics extensively. The P-38's configuration immediately appeared unconventional relative to German design practices. The aircraft employed a twin-boom layout with engines mounted on booms extending aft from the wings, supporting twin vertical stabilizers. The cockpit and armament occupied a central nacelle between the engine booms. This arrangement differed fundamentally from German twin-engine fighter designs, like the Bf-1T, which used conventional fuselage layouts with engines mounted on or in the wings and a single vertical stabilizer. Technical specifications documented in the dossier identified the power plants as Allison V1710, liquid-cooled V12 engines, each rated at 1,475 horsepower. The engines employed counter-rotating propellers. The right engine's propeller rotated clockwise when viewed from the cockpit, while the left engine's propeller rotated counterclockwise. This configuration eliminated asymmetric torque effects that created handling difficulties in conventional twin-engine designs with some-rotation propellers. The aircraft's construction methodology revealed significant differences from German manufacturing practices. External skin panels employed flush riveting rivets set so their heads did not protrude above the skin surface, reducing aerodynamic drag. Panel fits showed minimal gaps or irregularities. Surface finish approached machine-to-part quality rather than hand-assembled aircraft appearance. Jabs examined engine cowling tolerances closely. Panel fits were consistently tight across the entire airframe. German aircraft production, based on his observation of Bf-2110 assembly at the Gotha facility, relied on skilled craftsmen hand-fitting panels, adjusting tolerances, and filing edges to achieve proper fits. This process meant each aircraft possessed slight individual variations. No two were exactly identical. The P-38's construction suggested component interchangeability at a level German production had not achieved. Becker confirmed this assessment, noting that American manufacturing philosophy emphasized precision mass production, using interchangeable parts requiring no hand-fitting during assembly. Armament configuration represented another significant departure from German practice. The P-38 mounted all weapons in the nose-on 20mm Hispano-Suiza autocannon and 4.50 caliber Browning M2 machine guns, according to Becker's documentation. This arrangement contrasted with German fighters mounting cannon and machine guns in the wings, requiring pilots to calculate convergence distances where streams from different mounting points would intersect. Nose-mounted armament eliminated convergence calculations. The pilot aimed the entire aircraft at the target, and all weapons fired along parallel paths from closely grouped mounting points. This simplified gunnery and improved accuracy, particularly at varying ranges. Wing-mounted weapons required pilots to engage targets at specific convergence distances, typically 300 to 400 meters for German fighters. Firing at closer or longer ranges meant that half or more of the weapon's fire would miss, even when the sight picture appeared correct. The 20mm Hispano cannon provided heavy anti-aircraft firepower. The Hispano-Suiza design, developed originally in Switzerland and manufactured under license in Britain and the United States, fired high-explosive shells effective against aircraft structures. The 4.50 caliber Browning M2 machine guns provided high volume of fire. The M2's cyclic rate approached 800 rounds per minute per gun, giving the P-38 approximately 3,200 rounds per minute combined rate of fire from the machine guns alone. German fighter armament typically consisted of 20mm MG-151 20th cannon and 30mm MG-131 machine guns in various combinations. Becker directed Jabs to the engine test facility to observe the most significant discovery from Rechlin's evaluation program. One of the P-38's Allison V1710 engines had been removed and mounted in a test cell for detailed analysis. Rechlin engineers had completely disassembled the engine, documenting construction methods, measuring all components, and analyzing manufacturing techniques and material specifications. The technical report Becker provided included flight test summaries documenting the P-38 single-engine performance characteristics. Test pilot Lieutenant Werner Hoffmann had conducted deliberate single-engine failure simulations at 6,000 meters altitude. The procedure involved shutting down one engine completely while maintaining flight on the remaining engine. Results documented in the flight test report indicated the aircraft maintained level flight with no significant loss of control authority. The test pilot's assessment described the P-38 as surprisingly manageable operating on single engine. Hoffmann's test profile extended beyond basic controllability assessment. Operating on one engine, he conducted a complete circuit pattern, climbed to 7,000 meters, performed combat maneuvers, including turns and dives, and executed a normal landing all without restarting the failed engine. The single-engine operation continued for approximately 90 minutes, demonstrating sustained capability rather than emergency-only performance. For Jabs, this performance represented a fundamental operational advantage. The Bf-110, his operational aircraft with 800 flight hours of experience, was effectively uncontrollable following single-engine failure. Asymmetric thrust from the operating engine created unmanageable rotational movement around the vertical axis. Standard procedure following Bf-110 engine failure called for immediate bailout rather than attempting single-engine landing. Jabs had personally lost 3 squadron members to engine failure-experienced pilots who died because the Bf-110 could not sustain flight on one engine. Becker explained the engineering factors enabling the P-38's single-engine capability. The counter-rotating propeller arrangement eliminated torque asymmetry. In conventional twin-engine designs, with semi-rotation, engine torque and propeller effects created rolling and yawing moments that differed between left and right engines. When one engine failed, these asymmetric effects combined with asymmetric thrust to create control problems. Counter-rotating propellers balanced these effects, making single-engine flight more manageable. The twin-boom design contributed to single-engine capability through symmetric weight distribution. Conventional twin-engine designs concentrated fuselage weight on the centerline with engines offset to either side. This symmetry amplified control difficulties during single-engine operation. The P-38's distributed structure balanced weight more evenly, reducing control forces required to maintain directional stability. The vertical stabilizers, one on each boom, provided exceptional directional stability. Their large surface area and positioning at the boom's trailing edges created powerful stabilizing moments. During single-engine operation, the vertical stabilizer on the operating engine's side helped counteract yaw from asymmetric thrust. Engine mounting geometry proved equally important. The Allison engines were positioned close to the fuselage centerline relative to conventional twin-engine layouts. This reduced the moment on the perpendicular distance from the engine S thrust line to the aircraft S center of gravity. Shorter moment arms meant asymmetric thrust from single-engine operation created smaller yawing moments, making the aircraft easier to control. Becker noted that Bf-110 engine mounts varied between individual aircraft due to hand-fitting during production. Each aircraft possessed slightly different weight distribution and engine alignment, contributing to variations in handling characteristics. The P-38's standardized construction ensured consistent engine positioning across all aircraft, making single-engine handling predictable and training appropriate. The design philosophy comparison was striking. German engineering had optimized the Bf-110 for maximum performance speed, climb rate, and combat effectiveness, assuming engines would operate reliably. American engineering had designed the P-38 assuming engine failures would occur, incorporating redundancy and survivability into the fundamental airframe design. In combat operations, where mechanical reliability directly affected survival rates, the American approach proved superior. Pilots flying aircraft designed for redundancy survived engine failures that would kill pilots in aircraft optimized solely for performance. Becker transitioned the briefing to strategic implications by spreading maps across the conference table. The P-38's combat radius, the distance an aircraft can fly from base, conduct combat operations, and return, represented its most significant operational characteristic from a strategic defense planning perspective. Technical specifications documented in the evaluation report indicated the P-38's combat radius as approximately 650 miles when equipped with external drop tanks, or 450 miles using only internal fuel. These figures derived from fuel capacity, engine efficiency, cruise speeds, and reserve requirements for combat maneuvering. A 650-mile radius from English bases covered all of occupied France, Belgium, Luxembourg, Netherlands, most of Western Germany, and portions of central Germany, including major industrial areas. Jabs studied the map with growing concern. A 650-mile combat radius represented triple the operational range of Germany's best single-engine fighters, the Messerschmitt Bf -109He. The Luftwaffe's primary fighter achieved approximately 350 miles combat radius when equipped with a 300-liter drop tank The Focke-Wulf FW-190A achieved approximately 320 miles. The Bf-110G, despite being a twin-engine design, managed only 450 miles maximum, matching the P-38's internal fuel range, but falling 200 miles short of its drop tank range. Becker illustrated the implications using concentric circles drawn on the map. The inner circle, representing German fighter radius from Luftwaffe bases in occupied France, covered only northern France and the Low Countries. The outer circle, representing P-38 radius from English bases, covered essentially all of German-controlled Europe west of Poland. American fighters operating from Britain could escort bomber formations to Berlin, Munich, or any other target within the Reich. This capability rendered obsolete German fighter tactics developed since 1940. Luftwaffe defensive doctrine relied on intercepting bomber formations beyond escort fighter range. German fighters would climb to altitude, attack bomber formations from advantageous positions, inflict casualties, and break off engagement before short-range escort fighters arrived. This approach had proven effective against RAF daylight raids in 1940-1941, forcing RAF Bomber Command to shift to night operations, where escort fighters could not operate effectively. If American fighters could escort bombers throughout their entire mission profiles, there would be no beyond escort range phase where German fighters could attack freely. Every interception would occur against bomber formations with fighter protection. This fundamentally changed the tactical situation from advantageous interception of undefended bombers to dangerous engagement against protected formations. Becker provided detailed fuel system analysis, explaining the P-38's endurance advantage. The aircraft carried 410 gallons of internal fuel in wing tanks, and the centralness to 150-gallon drop tanks external fuel tanks, jettisoned when empty or when entering combat, provided additional 300 gallons, giving 710 gallons total fuel capacity. The Allison V1710 engines demonstrated remarkable fuel efficiency at cruise power settings. Specific fuel consumption: the pounds of fuel burned per horsepower produced per hour, 0.48 pounds per horsepower at cruise power, according to Allison's engineering data. At 25,000 feet altitude, cruise power settings of 1,200 RPM and appropriate manifold pressure, each P-38 engine consumed approximately 40 gallons per hour, giving combined consumption of 80 gallons per hour for both engines. With 710 gallons total fuel capacity and 80 gallons per hour consumption rate, the P-38 could remain airborne for approximately 8.8 hours. At cruise speed of 290 miles per hour, this yielded maximum range of 2,550 miles. Combat radius accounting for fuel reserves required for combat power settings, tactical maneuvering, and safety margins was calculated as approximately 650 miles, roughly 25% of maximum range, a standard military planning factor. Comparable calculations for the Bf-109G revealed the disparity. The German fighter carried 88 gallons internal fuel with a 66-gallon drop tank, totaling 154 gallons, less than 22% of the P-38's capacity. The Daimler-Benz DB605 engine consumed approximately 72 gallons per hour at cruise power. This gave endurance of approximately 2.1 hours at 280 miles per hour cruise speed, yielding 590 miles maximum range. Combat radius of 350 miles represented approximately 59% of maximum range, a higher percentage, due to the single-engine fighter's lower fuel reserves compared to twin-engine designs. The numerical comparison was devastating. The P-38 carried 4.6 times more fuel than the Bf-109G. It achieved nearly triple the combat radius, and this capability was installed in a twin-engine airframe that could survive single-engine fare in event that would kill a Bf-109 pilot if it occurred over enemy territory. Becker outlined the tactical implications through a hypothetical engagement scenario. If 100 P-38s escorted a bomber formation to Berlin and the Luftwaffe scrambled 200 Bf-109s to intercept, German fighters would have approximately 15 minutes of combat time at the target area before fuel state required breaking off and returning to base. The P-38s could remain over the target for 90 minutes, 6 times longer. The engagement timeline Becker described revealed the mathematical certainty of attrition warfare. German fighters would attack, expend ammunition, and withdraw due to fuel limitations. Fresh P-38s from other formations would remain on station. Additional German fighters would scramble, engage briefly, and withdraw as fuel became critical. Meanwhile, American escorts maintained continuous presence. By the time bomber formations completed their bombing runs and began egress, German fighters were grounded for refueling, while P-38s still possessed adequate fuel for the return flight. Germany would face a situation where tactical victories destroying individual bombers, or American fighters, became strategically meaningless. The Americans did not need to win fighter versus fighter engagements. They only needed to remain present, forcing German fighters to burn fuel maneuvering and engaging until German fuel exhaustion ended the threat. Endurance, not combat performance, became the decisive factor. Becker directed Jabs to a secured analysis room where tables held production reports, intelligence, summaries, and reconnaissance photographs classified at the highest level. Reich Minister Albert Speer's office had compiled this data from multiple intelligence sources, including human intelligence from neutral countries, signals intelligence, and photographic reconnaissance of American industrial facilities. The folder marked Geheim, U.S. Aircraft Production 1943 contained detailed production statistics. American manufacturers had produced 10,037 P-38 Lightning aircraft between 1941 and August 1943, according to intelligence estimates. Current production rate at Lockheed's Burbank, California facility approximated 200 aircraft per month. Jabs calculated the annual production rate, 2,400 P-38s per year. Becker provided German production figures for comparison. Messerschmitt facilities were producing approximately 150 BFF 110 twin-engine fighters per month, 1,800 annually. The production ratio appeared concerning but not catastrophic. America was outproducing Germany in twin-engine fighters, but the margin seemed manageable. Becker's expression indicated this assessment was incomplete. The P-38 represented only one of multiple American fighter types in production. Republic Aviation's P-47 Thunderbolt production reached approximately 350 aircraft per month. North American Aviation was ramping P-51 Mustang production to 400 per month. Curtiss-Wright continued producing P-40 Warhawk fighters at approximately 200 per month, despite that design being somewhat obsolete. Becker compiled the numbers on a chalkboard. American fighter production, August 1943. P-38 Lightning, 200 per month. P-47 Thunderbolt, 350 per month. P-51 Mustang, 400 per month. Projected P-40 Warhawk, 200 per month. Total, 1,150 fighters per month. 13,800 annually. German fighter production, August 1943. Bf-2 109, 1,000 per month. F-190, 450 per month. Bf-110, 150 per month. Total, 1,600 fighters per month. 19,200 annually. German production appeared to exceed American fighter production by approximately 28%. However, Becker noted this comparison was incomplete and misleading. The critical difference appeared not in finished aircraft totals, but in underlying industrial capacity and production methodology. Becker presented engine production data, revealing the true scale disparity. The P-38 used Allison V-1710 engines, manufactured at Allison Engine Company's Indianapolis plant. This facility produced V-1710 engines for multiple aircraft types simultaneously. P-38s, P-40, SA-P-39, Aerocabras, and P-6. Monthly production exceeded requirements for P-38 assembly, with surplus engines supporting other programs or stockpiled as replacement units. The P-47 Thunderbolt employed a completely different engine, the Pratt & Whitney R2800 Double Wasp, an 18-cylinder air-cooled radial engine displacing 2,800 cubic inches and producing 2,000 horsepower. This represented substantially more power than German engines. The DB605 and the Bf109G produced approximately 1,475 horsepower. The BMW 801 and the FW190A produced approximately 1,700 horsepower. Pratt & Whitney operated multiple facilities producing R280R engines. The main plant in East Hartford, Connecticut, and additional facilities in Kansas City and other locations achieved combined output exceeding 2,000 engines monthly. These engines powered not only P-47s, but also F-6F Hellcat naval fighters, F-4U Corsair naval fighters, and various bomber and transport aircraft. The implications crystallized for Jabs. American industry was not simply producing more aircraft. It was building redundant production capacity with multiple engine types, multiple airframe manufacturers, and distributed facilities. Destruction of one factory would inconvenience production but not halt it. 10 other facilities would continue operating. German industry concentrated production at fewer, larger facilities vulnerable to disruption. Becker presented the information that most concerned Reich Minister Speer, comparative industrial capacity assessments based on reconnaissance photography and intelligence estimates. He showed aerial photographs of American aircraft factories. The images revealed vast assembly halls with production lines extending hundreds of meters. Willow Run, Ford Motor Company's bomber plant in Michigan, produced one B-2 for Liberator heavy bomber every 63 minutes, according to intelligence estimates. Boeing's Seattle facility achieved similar production rates with B-17 Flying Fortress bombers. Additional photographs showed consolidated aircraft in San Diego, Douglas Aircraft in Long Beach, North American Aviation in Kansas City, and Lockheed in Burbank. Each facility appeared massive by German standards. Becker noted that American aircraft production occurred at dozens of such facilities operating simultaneously. The final photograph and aerial reconnaissance image of the Willow Run plant provided the most striking comparison. Becker stated that this single facility covered more floor space than all of Messerschmitt's combined production facilities, and America possessed dozens of factories approaching this scale. This revelation completed Jabs' understanding. The evaluation was not fundamentally about assessing a captured P-38's technical characteristics. It was about determining whether Germany could win an industrial war against the United States. The conclusion was already calculated through basic arithmetic. Germany could not match American production capacity, regardless of how efficiently German industry operated or how skilled German workers were standing beside the P-38 on Rechlin's tarmac during the afternoon of August 17, 1943. Jabs synthesized the information Becker had presented. The production figures appeared favorable on paper. German monthly fighter production of 1,600 aircraft exceeded American production of 1,150 fighters. Yet Jabs understood why these numbers were misleading. German aircraft production required skilled craftsmen, workers hand-fitted components during assembly, making custom adjustments to achieve proper tolerances. Each aircraft emerged slightly different from every other, with individual variations in weight distribution, control response, and performance characteristics. Production rates were bottlenecked by craftsman availability. Increasing output required training additional skilled workers, a process requiring months or years. American production employed fundamentally different methodology. Interchangeable parts, manufactured to precise tolerances, required no hand-fitting during assembly. Unskilled or semi-skilled workers could perform assembly operations following standardized procedures. Production rates were bottlenecked only by raw material availability. Steel, aluminum, rubber, copper, and America possessed abundant natural resources, plus access to global markets through control of Atlantic and Pacific sea lanes. The P-38's design reflected this production philosophy. Components were standardized and interchangeable. Thrust, riveting, and tight tolerances resulted from precision manufacturing rather than hand-fitting. The aircraft was designed for mass production by semi-skilled workers using standardized procedures, not for construction by master craftsmen exercising individual judgment. German fighters represented opposite philosophy. The Bf-109 and Fw-190 were superb aircraft when properly built by skilled workers, but their construction required craftsman skills that took years to develop. Production expansion was limited by skilled worker availability. Bombing of German cities killed experienced workers and disrupted training programs. The replacement workers lacked experience, leading to quality variations and reduced production rates. The P-38's twin-engine redundancy design similarly reflected American production philosophy. German engineers optimized aircraft for maximum performance, assuming components would function reliably. American engineers designed systems, assuming components would fail, incorporating redundancy to ensure survival when failures occurred. This approach made sense for a nation with vast production capacity building slightly larger. Heavier, more complex aircraft was acceptable if it improved survival rates because replacement aircraft could be produced readily. The 650-mile combat radius represented another aspect of American design philosophy. German fighters were optimized for point defense intercepting bombers near German targets, where short range was acceptable because bases were nearby. American fighters were designed for escort missions requiring extended range to accompany bombers to distant targets and return. This capability required larger fuel tanks, reducing performance but increasing mission flexibility. The R2800 engines. Mass production 2,000 units per month contrasted sharply with German engine production. The DB605 engine, while excellent, required skilled engine builders for assembly. Production approached 1,500 monthly, but quality control problems emerged as production accelerated and less experienced workers were employed. The R2800's design facilitated mass production using interchangeable parts and semi-skilled labor. These comparisons revealed an inescapable conclusion. Germany was fighting a quality versus quantity war, and quantity possessed its own quality. American aircraft might be less refined than German designs, but they were produced in numbers that made individual aircraft quality irrelevant. If America could produce 10 fighters for every one Germany produced, German fighters needed to achieve 10-to-1 kill ratios merely to maintain parity. No air force in history had sustained such performance. Jabs possessed 50 confirmed victories. He was among the Luftwaffe's elite pilots. But if American factories produced fighters faster than he could destroy them, his skill was strategically meaningless. He might shoot down 10 American fighters in his career. But if America produced 100 replacements monthly, his victories accomplished nothing toward winning the war. The endurance disparity compounded this problem. If American fighters could remain over targets for 90 minutes, while German fighters had 15 minutes of combat time before fuel exhaustion forced withdrawal, tactics became irrelevant. German pilots might execute perfect interceptions, but they would be forced to break off engagement while American escorts remained, allowing bomber formations to proceed to targets. If American bombers could strike any target in Germany with fighter-esque Munich, industrial Ruhr, anywhere air, defense became impossible. The Luftwaffe would face simultaneous raids against multiple targets, forcing dispersion of fighter forces. Some targets would receive inadequate defense. Production facilities would be damaged. Worker morale would decline. The cumulative effect would be industrial collapse, regardless of how well individual German fighters performed in combat. Becker arrived in a staff car. As Jabs completed his analysis beside the P-38, the senior technical officer requested Jabs' operational assessment, the conclusion that would be forwarded to Luftwaffe High Command and possibly to Reichsmarshal Göring personally. Jabs' response, as later documented in Rechlin evaluation reports, acknowledged the P-38's tactical weaknesses. The aircraft's twin-boom configuration created visibility blind spots. Its size made it less maneuverable than single-engine fighters. A skilled Bf-109 pilot employing sound tactics could exploit these characteristics in individual engagements. In 1 vs 1 combat, German fighters retained advantages. However, Jabs emphasized that tactical considerations had become strategically irrelevant. What mattered was not whether German fighters could defeat individual P-38s in combat. They could. What mattered was that American industry could produce 200 P-38s monthly. What mattered was that American engineers designed aircraft to survive engine failures that would kill German pilots. What mattered was that American fighters possessed sufficient range and endurance to escort bombers throughout entire missions to any target in Germany. The assessment continued that Germany faced an adversary that did not need to build superior aircraft. America only needed to build more aircraft than Germany could destroy, and American industrial capacity made this achievable. The Willow Run factory alone, producing one B-24 bomber every 63 minutes, generated more heavy bombers monthly than the Luftwaffe could destroy, even if every intercepted bomber was shot down. Becker acknowledged this, represented the assessment Reichsmarshal Göring required from operational pilots rather than test pilots or engineers. Engineers could document technical specifications and performance characteristics. Only combat pilots could evaluate strategic implications based on operational experience. Whether this assessment would influence strategic decision-making remained uncertain. Becker's expression suggested that senior leadership was not receptive to pessimistic evaluations, regardless of supporting evidence. Jabs returned to IVN JG-1 3 days later, resuming night fighter operations. He flew 47 additional combat missions between August 1943 and war's end, achieving 28 more confirmed victories for a total of 78. He survived the war, unlike many Luftwaffe pilots who continued operations into 1945, despite diminishing aircraft availability, fuel shortages, and overwhelming Allied air superiority. But on August 17, 1943, standing beside a captured American fighter at Rechlin Test Center, Jabs understood something fundamental about the war's trajectory. Tactical skill and individual courage were becoming strategically irrelevant. Germany was fighting an industrial war against an opponent possessing overwhelming material superiority. American production capacity exceeded German capacity by orders of magnitude. American design philosophy prioritized reliability and survivability over peak performance. American operational doctrine employed their industrial advantage to overwhelm German defenses through attrition. The mathematics were inescapable. Germany could win individual battles while losing the strategic war. German pilots could achieve impressive kill ratios while still being overwhelmed by replacement aircraft. German fighters could perform superbly while being defeated by enemies that remained on station longer, flew farther, and survived damage that would destroy German aircraft. By August 1943, more than a year before D-Day, 21 months before the Battle of the Bulge, 33 months before German surrender, the war's outcome was already determined by industrial capacity and resource availability. Germany lacked the production capacity to replace losses at rates matching Allied aircraft production. German fuel supplies were inadequate for sustained operations. German pilot training programs were producing inadequately trained replacements, as experienced instructors were reassigned to combat units. The P-38 evaluation revealed these realities through concrete, technical, and industrial comparisons. American aircraft design, philosophy, production methodology, and industrial capacity represented systematic advantages that tactical excellence could not overcome. Germany had already lost the air war by August 1943, though fighting would continue for another 21 months until May 1945.